All right, I think we're here. Um, we've got a couple of things to do today. One, we've got to look at microphone sensors. Well, actually, this one's a prepackaged one that's not in your kit, but I'm just going to show it to you also, in case some of you might be using that one for your project. We're also going to look at random uncertainty. So uncertainty in measurements you take. We've already looked at this some, so it might seem redundant, but this is a little bit different. And we're going to look at, what else? We're going to look at something else. Oh, sampling rate. So some signals we just can't measure, or we're going to have to use different tools to measure at least because of this thing that we have to deal with called sampling rate and frequency of the signal. All right, let's just start with the microphone since it's sitting here. You have this microphone. Let's get a closer look at it. Let's see, there it is. All right, you've got this microphone. I've got it in a circuit. Let's show you the circuit right here. You don't have to, you've got this somewhere else that you can download it if you want to look at this, but basically we're still doing analog pin. Now that says analog pin 1. I think I actually have it in 0. Yeah, have it in 0. So obviously you'll have to change the code to read pin 1 or 0. This little symbol right here with the 2 parallel lines, that's a capacitor. So that's a 10 nanofarad capacitor. In our circuit, it's this little guy right there. We've got a 10,000 ohm resistor, so that'd be brown, black, orange. So right here, brown, black, orange. And then we've got a 1 mega ohm resistor, so that's brown, black, green. So you do have one of those in your kit right here. They don't look any different other than it's got a green line on it. Then you've got the microphone itself. The microphone does have a positive and negative, although they're not really labeled on here. If we get it out, you can kind of see maybe how this leg has these little connection points to this outer shell. That's the ground one. Sometimes, let's see if I can make it zoom or focus on that. Here we can zoom into it. There we go. You can kind of see it there. These little lines coming out to the outer shell, the metal casing, that's the ground leg. And ground is going to be connected to this green wire right here, ground. So let's zoom back and see if I can get it back in there. There we go, like that. Now this one is pre-packaged, so it's the same microphone, but it's already got a little signal conditioning circuit on here. Or actually, maybe that's an A to D conversion, because this one can put out analog or digital outputs. This is only analog output. Looks like we have a potentiometer for tuning something, a couple of resistors, capacitors built in. So it's basically the same thing, but a little bit nicer, and it can output an analog digital signal. So there's an A to D conversion on this one. I haven't actually used this one, I just had it, so I thought I would show you that they do come pre-packaged in a little board also. I haven't tried, we might try plugging this one in and see what it looks like on the same code that this one is. Basically, all we're going to do is we're just going to run Arduino code. See if I can get that pulled up here. And we're going to start a serial communication so we can do the serial. Actually, we're going to do a serial plotter this time, not the monitor, so we can actually see a little graph of the thing. We're going to leave these out. This would just print the timestamp and a comma. Since we're trying to measure something related to sound, that's a higher frequency generally. So anything that we don't have to do, we're going to leave out. So we're not going to print these timestamp and comma to our serial monitor. Well, we're going to the plotter anyway. Here's our analog read. Oh, you know what? That's on analog read 1. I'm pretty sure I have this plugged into 0 though. Yeah, let's plug it into 0. All right, and delay, well, that says 100 milliseconds. Let's put it back to 100. Let's plug in our Arduino, upload this code, and see what we get. All right, so if we open our serial plotter, There we go. So you get a little bit of a, you can barely see it down there, but it hears me every now and then if I make a sound above it or tap it or something, you see a spike in the number. So remember the number here is it's related to the voltage. We have it powered by 5 volts and we're doing analog read referencing 5 volts. So that if this number on the y-axis got to 1023, that would be 5 volts. This little peak right here is almost 2.5 volts, or right at 2.5 volts maybe. Now it does look like there's a periodic signal that it's detecting here. That may not be a sound. That is probably something with this charging capacitor in here. Let's see if we can speed it up. So let's close that down and let's drop this down to 10 milliseconds just to see what it looks like. Uploading plotter. Obviously the little thing is going to go by faster. So need it to scale. It's a lot noisier, so all this little jagged stuff is noise in the signal. Basically it's detecting that noise is there or not. It's not necessarily giving me information about, like if I was trying to play a certain note or whatever. Now this thing auto scales. I don't know if I can make it, I don't think I can make it not auto scale. So at least with the built-in serial plotter. So it dropped back down. It looks like there's all kinds of stuff there, but it's really that it changed the y-axis every time the things went off the screen, scrolled off the screen. So it's not really giving me signal information as far as what frequency is this thing, but it does tell me that there's a sound detected or not. Now it doesn't have a whole lot of range unless it has to be a really loud sound. You know, it just doesn't detect much beyond right in front of it. Like if you're right on top of it, it can detect it. Let's see. And obviously we could change the delay to essentially 0. The analog read itself has a little bit of a delay built in. And then the fact that you're printing to the serial monitor also is actually a pretty significant delay in terms of computing time, having to send characters to the monitor. All right, let's look at this guy. I haven't actually connected this, but if you look at it, it says there's analog out, there's ground, there's power, and this one is digital out. So I think if we just connect these 3 to power, ground, and analog out, we should have something. So let's see. Power is that one, ground there, and then we'll, all right, so it came on that it's got an LED on it. Let's move our analog out over here. And let's run our same exact code and see. I have no idea, but let's just see. It may blow up, but if it does, it's really small, so it's not going to do much. All right, so there's a signal like we had before. It's not nearly as noisy as the other one was. And we get a similar, you know, similar type of effect. Here's what we were looking at. It doesn't seem to be as sensitive, although it does have this potentiometer, which I assume if I had a way to turn that, which it's super tiny, I could adjust the sensitivity to it. But the signal is much, much cleaner than the one that we had over here. So basically I'm doing the same thing where I tap it and you can see little spikes in it. Still don't think you could get frequency, like what if I was playing a note, if we could detect that note, unless it was a super low note and I was right up on top of it. Maybe like with a tuning fork or something right on top of it, might be able to detect that. But again, we have to talk about this sampling rate thing that we would run into, which we'll talk about later today. So these are both sound detectors. I don't know that you could necessarily call them like frequency, where you get actual note information out of them or sound information, but you can detect the presence of a sound right on top of them. Right on top of them though. So, and this one I think we could probably adjust with this potentiometer. I just don't have a little tiny screwdriver up here to mess with it. Just wanted to show you those. This one is very easy to connect. It's just the 3 wires, and it does have that digital out that I didn't even try. This one's not more necessarily hard to connect. It is noisier, so this one does have some kind of signal processing on it that is making it cleaner. This one is relatively noisy, but it's, you know, these are super cheap components, and you have all of these components in your kit ready to go. The circuits, you know, it's not bad. Where is it? Right here. Right here is the circuit for building your own microphone sound sensor. There is a sketch over here that basically it will tell you to snap your fingers, or that's why I call it snap, or make a sound or whatever, and it will measure the time between when it told you to do that and when you actually did that, and so it kind of gives you your reaction time thing. All right, so that's how those work. Now let's go over, let's unplug my Arduino so it's not just sitting there in the way. Get it out of the way. Wow, it's wrapped around everything. Just move that. All right. We said we were going to talk about uncertainty analysis again. So let's start that. This idea of random uncertainty. All right, I'm just getting all my stuff ready. All right. So we have this idea that we have been calculating uncertainty, and it was always that we had this true value in mind, and we don't actually know this true value. If we knew the true value, then there really wouldn't be a point in measuring anything because we know what the value was. So we have to kind of remove this idea that we actually know the true value. Maybe we have what the true value is supposed to be, or, you know, particularly if it's a physical measurement, then we designed it to be a certain way, and we're trying to measure if it is. Or maybe we have taken a lot of measurements in the past, and we have this idea that the true value is over here or somewhere. We know what it is, at least after repeated measurement. Maybe that exists. There's always going to be some kind of bias, systematic error. You know, you didn't zero your calipers. You know, you didn't get, when you closed them up, you didn't get the little knob dial to zero. It was off a little bit. Maybe you didn't do that. That would be a bias or a systematic error. Maybe your ruler doesn't start at 0. You know, kind of, maybe it doesn't actually have the right end on it. Or maybe it's one of those, or maybe it's like this end where there's some material and then the gauge starts and you're not using it that way. Maybe there's a offset that way. So there's always some kind of potential for bias or systematic error. And then there's all the random stuff that happens, like you take the measurement 3 or 4 times and you get 3 or 4 different numbers. So we have to combine these. If we took a single measurement, so just one measurement, then what we could say is that the random uncertainty, remember, oh, I forgot this. We called B the bias error, and we called P the uncertainty. I think it's what we used. Or random, we called it random, let's call it that. And so this was the systematic and this was the random error. So the random error, or the uncertainty in a single measurement, so if we took one measurement, is equal to plus or minus t, so that's your, remember the t distribution for small sample sizes, 1 would certainly be a small sample size, times the standard deviation of that sample. So you would have to have a whole bunch of, you'd have to have some information about the standard deviation. The problem is, if you only took one measurement, you can't calculate. You can't take your T chart, doesn't work for degree of freedom 0. You know, here's one. Degree of freedom starts at 1. So that means you at least took 2 samples. So we couldn't actually do T, and you can't calculate a standard deviation for one sample. So one way that we deal with this is we use a standard deviation from a previous sample. So maybe you've already taken measurements before and you have this information about standard deviation, still sample standard deviation. If you calculate the standard deviation from a large sample, so greater than 30 is what we set as our cutoff. You know, there's some people will say greater than 40 or whatever, but if we look at our t-table, a lot of times, let's look at it here. So a lot of times, once you get to 30, you'll see that these numbers, well, they continue to change, but they're not, well, actually, I guess you'd be at 3129, I suppose, because it's degrees of freedom on here. But they start to slow down their rate of change, I suppose we could say. Then even the tables themselves begin to not give you incremental data. It goes from 30 to 40 and then 40 to 60, and then here it is at 1,000, and you're not getting that much change anymore once you get to about 30 samples. So we're going to say if you took your sample n is greater than 30, at that point you're in the normal distribution range of things, and you can just say, for this purpose of this equation, we'll put it over here. I might need to find a better writing pen. Let's see about this one. T, there we go, equals 2. So this t, the t value, once you get to n greater than 30, or maybe even equal to 30, you can just assign t a value of 2. You don't have to go to the chart and look it up. You can just say that t equals 2. All right, so that obviously, if you have one sample, that's not going to really work. But if you have 30 or more, then t can equal 2. All right, so this is for one sample. If we did have more than one sample, to find the random uncertainty of a mean value, an average value, is equal to plus or minus t times that standard deviation over the square root of the number of samples. So again, this square root of one sample would be square root of 1, so it'd be over 1, which sends you back to this equation. But this one would be more than one sample. Okay, and we've seen this before. We saw this kind of thing last time. So let's try and draw what this is telling us. So here's our baseline, and we're going to put a orange. Guess we need a little longer. All right, let's say that the true value, just to put it somewhere, let's say that this is our true value. So we're off from our true value for some amount. So this is our systematic offset. If we went in, found the mean of this distance is what we've been calling B. So that's the distance where you didn't calibrate your calipers, or you didn't measure correctly, or you've got your gauge needle is bent, something, I don't know. But that's that systematic offset or bias offset. It just shifts the mean of everything you measured away from the true value. If we took, now this one I'm going to put is not in a specific spot. I'm just putting it out here so that we can label it. If we took a single measurement and that's where it landed, so it's this one right here. On either side of it, there is some amount of random error that we don't know about, and we only took one sample, so we're saying that it's plus and minus. So somewhere over here, this would be P, and somewhere over here, this would be a distance P. So that P is this random uncertainty. So T times our standard deviation gives us something like this. This is one measurement. And so it's got a relatively wide uncertainty around it. It should still land somewhere within the distribution if we had a bunch of samples. It is possible that it would be outside, because there is some chance that it exists out here. But this range is the amount of uncertainty that is associated with this one measurement. If we did the same thing, let's use a different color, blue. I'll put it somewhere not overlapping everything, I guess. If we took multiple samples, maybe they land over here. So this is the mean of multiple samples. They too have an uncertainty associated with them, but it's the same thing as a single uncertainty, but divided by the square root of how many times we took that measurement. So it's smaller. So it has the same idea here, except that its range might only be, you know, here to here. So it's a little bit narrower than it is when we only take one. And the more and more samples you take, the more you're narrowing down this uncertainty, because you're increasing the denominator in this equation that calculates the uncertainty. So the more samples you take, and the more samples you take, the t-value changes. Also, it gets lower and lower. Remember our chart. If I find our chart, here it is. The top part of the chart is, and normally we're in the 0.05 or the 0.025. This one has both on it, so it has two tails and one tail. That is talking about tails, you know, one tail or two tails on either side. Most of the charts that we've been looking at up to this point were just one-tailed, so we had to do the alpha over 2 thing. This one just puts them together in case you, I don't know, forget how to divide, I guess. But we're looking at this chart, and at the top of the chart is fewer samples, 1 degree of freedom, so that's 2 samples. And notice T is 12, and then 4, and 3, and 2, and then it eventually gets down to where it's basically just 2. It becomes essentially 2. So not as you have more and more samples, not only are you increasing this denominator, but you're decreasing this value for T. So the effect of more and more samples is that you reduce this uncertainty around the measurement that you're making. All right, let's get back to this thing. There's a write-up that on Moodle that you can read more little details about this. So if we had the total uncertainty, so the total uncertainty would be the fact that there's some bias, there's some offset, and then the measurement, whether it's a single measurement or a group of measurements, they have their uncertainty associated with those. So the total uncertainty, let's do for xi, so that's for a single measurement that you make. Any single measurement, you could even say this is the uncertainty for a single measurement among a group of measurements. That'd be fine too. But it's for any individual measurement is equal to the square root of b squared, so there's some offset, plus p, and we'll label these pi over here since they are for individual measurements. I guess if we pxi, so the probability for an individual measurement, not just I. Let's put an x in there. There we go. And it's squared also. So it's the way that we combine a lot of things. You know, you square them, add them together, and take the square root of them. That would be the total uncertainty, this thing, total uncertainty for a single measurement. So whether or not you took a whole bunch of measurements and you're interested in the uncertainty around a individual in that group, or you only took one. Now, if you only took one, then this probability does include T and S in there, so you have to have some way to get those numbers, maybe from a prior data set or something like that, or you have other information about that. And you would have this similar equation, and we're going to call this one X bar, so that it's a mean of multiple samples. And it looks exactly the same, except B is the same because it's the same offset, the same bias. Plus, now we'll have the probability of that sample. So we'll put this as I use blue, X bar. Okay. And so this would be the total uncertainty for a group of measurements, or for the mean of a group of measurements. So here you've taken, I don't know, 10 or 15 measurements. You've calculated their mean, you calculated their standard deviation and a t value from the chart, and you've calculated the probability or the uncertainty around that mean, and then you've combined it with this offset that you may or may not know about. The offset you would have to know from a bigger data set or from some other information. So for instance, here's what we might do. We have this example where we're estimating the heating value of natural gas, so the kind of gas that you might burn in a furnace or whatever. We take 10, 1, 2, 3, 4, 5, 6, 7, 8, and 10 samples, and they are these numbers. So the heating value, we'll just call it HV. We take 10 samples, and they are 48, 5, 30, 48, 9, 80. These are all in kilojoules per kilogram. 502, 10. The units don't necessarily matter for what we're doing, unless we were combining these with some other numbers where the units did matter. But right here, we're just comparing them to themselves. Hopefully I'm writing all these down right without skipping one. I keep looking back and forth, so I'm probably going to skip one. And we're going to run over down here. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think we got them all. All right. So we took a calorimeter and we measured the heating value 10 different times. So it's not a large sample. We didn't take 30 or more samples. So it's a small sample. So that means it's going to fall into the T distribution range of things. The calorimeter itself, we have a certificate of calibration for this thing. It's a nice piece of equipment, and we know that according to the manufacturer, the calorimeter, how do you spell calorimeter? Has a accuracy of 1.5% of the full range. Now this is a little bit different, the full range. The previous ones, I'm pretty sure all of the errors that we did were of the value itself, so like 5% of the value that was read. This one is stated a little bit different, so this is another type of error, the way to describe error that you might see, where it's the accuracy of some percentage of the full range. So that means you have to know what is the full range of the calorimeter. So this calorimeter can measure, and this is from the data sheet on the calorimeter. Whether or not it's true numbers, I don't know, but that's what we're going to use. From, whoops, left after R, from 0 kilojoules per kilogram up to 10,000, or no, 100,000, because these are all 50,000. 100,000. So that would tell me, this being able to measure from 0 to 100,000 tells me that the range is equal to 100,000 kilojoules per kilogram. And then I can take 1.5% of this full range. So from 0 to this, sometimes it goes from a negative number, or maybe it only goes from 20,000. So you figure out the range of what the instrument is capable of measuring when it tells you the error is associated with the full range. And so our full range is 100,000 kilojoules per kilogram. Accuracy of 1.5% means that our error is going to equal 1,500 kilojoules per kilogram. So 1.5% of 100,000. All right, so this is from the manufacturer. We don't know that it's necessarily, this is our uncertainty in any measurement we take. So this is related to, and we're going to call it the bias error, because it's coming from the tool itself, and it may not be, every time that it's off by 1,500, but every time it could be off by 1,500. So it's not exactly the way I described some of these, where if you track them down, like you didn't zero out your calipers, then you could track down that, I should just subtract that measurement. So this isn't quite like that, because we don't know that they're exactly off by 1,500 every time. That would be kind of silly, because then you could just subtract it off. But there's up to that amount of error, and we're going to call it the bias error. All right, what we're going to find or calculate is the random uncertainty for each measurement. So each one of the 10 measurements, what's the random uncertainty for that? Then we're going to find the random uncertainty for the group of measurements. So we take them as an entire group. And then assume that it's a large group, or at least we have a large group that has a standard deviation that equals this. So we're gonna calculate this standard deviation, and then whatever that is, we're gonna assign that to a large group. So that's not a real thing you do. We're doing that for calculating the equation later on. When we get to that, I'll explain it again. And then the total uncertainty. So combine the offset with the uncertainty for the measurements. All right. We could do this in Python. I'm trying to decide if I want to, or I think maybe we'll just do it by hand. If you want to do it in Python on Moodle, it does have all the Python code for doing it. The only thing I would say about that is that it does show you how to do a t-distribution in Python. We did that earlier, and you have to remember the PPF and the CDF and the whatever the other one is, PDF. You only need the PPF, so you have to kind of remember which ones are which if you're going to do it in Python. We're just going to use the charts. I'm going to use the t-table itself to do ours. All right. One nice thing about doing it in Python, though, is it is easy to calculate the mean and standard deviation of our data set. So we got to do that first. The mean is not a big deal. Mean equals, we add all these numbers up and divide by 10. Let's see. 48.5, I can't see it. 30 plus 48,980 plus 50,210 49,860 plus 48,560 plus 49540 plus 49270 plus 48850 plus 49320 plus 48680. Divided by 10. Our mean is 49180. That actually is the mean, so we did it right. And that would be kilojoules per kilogram also. All right, so that's the mean of our 10 sample set of measurements. We need the standard deviation also. That one I don't want to plug in, but remember we did have the equation for calculating standard deviation on an exam or anything like that. I'm not going to have you calculate the standard deviation of something that large of a sample set just because it's cumbersome. I'll either give you the standard deviation like I'm going to do here, or it won't be 10 samples. So the standard deviation comes out to be 566.3, also kilojoules per kilogram. So most calculators actually have statistics functions built in where you can build the list and then tell it to calculate the mean and standard deviation of the list. I didn't even bother to check on this calculator how to do that. All right. We would need to know how many. We need to know n, sample size. We already counted them. There's 10 of them. And then if there's n equals 10 samples, then the symbol for the degrees of freedom, we're just going to use df. Oh, well, df in Python is a lot of times used for data frame, a variable called data frame. But this is degrees of freedom equals 9 degrees of freedom. We'll do it this way. And now we can go to our t-distribution chart. Let me move some stuff out of the way so you can see it. There it is. Let's zoom in on it a little bit. All right, so we have 9 degrees of freedom, so we're down here at 9. And then we have all these columns. I don't know. Let me see if I don't think I said it. I did not. So if it's never mentioned what your level of significance is desired to be, you assume it's 95%, which would give us the this column right here. Either the two tails at 0.05 or the one single tail at 0.25. So it's this column, and we're at 9 degrees of freedom over here. So we find this value for t, 2.262. So there's our t value. Now, if you were in Python, then you could get this number using t-distribution ppf for that level of significance. Now, it does, remember, in Python, at least these libraries, this is the stats library, I think, statistics library, and the SciPy stats. Actually, it's the SciPy stats that does this, I think. I've lost the line. So it's SciPy stats that does it, and it measures a out of 1. So you have to do 1 minus your level of significance to get the actual number that you're looking for. So however you get it, if you're on an exam, you're going to get it the way we just did it. If you're on a computer or anything like that, you can use whatever that piece of software does to calculate your t value. So this is t for degree of freedom 9 and an alpha over 2 of 0.025, which would be 95% confidence. And again, if you're not told what confidence level to assume, then you assume 95%. The only reason you would use another column is if you're specifically told to use what is something else on here, 90% or 98% or some other one. That's the only time you would use a different column other than the 0.025 column. All right. So we have our t value. We can go now over here. Need our calculator to not fly away. And we can start doing this stuff. The first thing that we were asking for is the random uncertainty for each measurement. So that's for each means for one sample. So we have t. We have our standard deviation. I didn't calculate it. I just gave you the value for it. If you calculate the standard deviation of these 10 numbers, you would get this 566.3. So the random uncertainty for each measurement would be, let's get something I can write smaller. So this is P xi because it's for each measurement. And it doesn't mean that we go in and do each measurement individually. What it means is we calculate for one sample, all we need is t and standard deviation. So P, oh, not R, P xi equals plus or minus t, 2.262 times standard deviation 566 kilojoules per kilogram, and that equals calculator 2.262 times 566.3, 1280.97 kilojoules per kilogram. So any one of these measurements has that much uncertainty associated with it. That's what that's telling me. So if I were to, pick any individual measurement, this range here from the measurement over to where its maximum value might be and its minimum value might be, I'd have to add or subtract, oh, that should be a plus or minus, 1281 kilojoules per kilogram. So that's how 1281 would be that number, 1281 would be that number, and that would be the measurement I took. All right, then it asks, similar thing, I think we are trying to do the random uncertainty of the mean of measurements. So that's this equation where we have the same t value, we have the same standard deviation, except now we get to divide by the square root of n. This isn't degrees of freedom. Some people will actually make that mistake. This is n, the number of samples, so square root of 10. So it's going to be obviously be smaller, right? Because it's divided by square root of 10, where this number is not. So random uncertainty, and this one we called just px. I keep writing r's for p's. I don't know. Px bar for mean of measurements. Equals p. Wow, I don't know. I guess because I'm trying to get down there to write the x. Px bar equals plus or minus t 2.262 times the standard deviation 566.3 kilojoules per kilogram, but we divide by square root of 10. So it's this exact same number divided by the square root of 10. Still in my calculator, so divide by square root of 10, 405. P x bar equals plus or minus 405.1. And you can see that's the same thing that we had here with the blue, where maybe the mean is over here of the 10 measurements, and they have a smaller uncertainty around those because we've lumped 10 of them together, where any individual measurement might land in that or should land in that group, but it could be somewhere else. I probably should have made it where it lands inside the group, but I wasn't really planning this particular diagram to represent these numbers. All right, looks like we filled up that page. Let's see what else we're trying to find. The random uncertainty of the means of the measurements, assuming that S was calculated on a large sample. So standard deviation S. So assuming that this number came from, we took 50 measurements and got this standard deviation, what would be the random uncertainty of the mean based on this thing? So what changes here is just t right there. So instead of, this goes back to, did I write it down? Yeah. When n is greater than 30 or a large sample, then instead of going to the chart for t, you just say t equals 2. So it seems a little bit odd because you don't know necessarily to put square root of 10 in here, but this is kind of a, well, so this t and s, they can come from, the t and s have to come from the same set, right? So if s came from a large sample size, then t is for a large sample size also. And the mean that we're talking about here is from a separate sample. So I did a whole bunch of tests beforehand, found a value for s, and it turned out to be 566.3. And then I calculate the uncertainty associated with that, or at least the t distribution associated with that large sample is 2. So let's write this down before get too many things out on the page without, or too many things said without writing them down. So I took a large sample. Let's turn it straight. And for a large sample, when we're using the t distribution that we're using now to solve this equation, we say that t equals 2. And then we calculated the standard deviation for this large sample was 566.3 kilojoules per kilogram. It's not always going to be the same as the standard deviation for the sample that you take, the smaller sample. That's just the way we did it here so that you don't have to go find another number. So there's this t and s. Now I take the small sample and it has a mean, or x bar, equal to 49180 kilojoules per kilogram and an n of 10. So I've got, this is my 10 sample size, the one that's written here, right there. But I already know this information from a larger sample. So what I can do there is that I can say, oh, well, the probability P, or not the probability, but the random uncertainty P for a mean that I have here equals plus or minus t times standard deviation over square root of n. But I can take the t of this large sample, since I'm using the standard deviation from a large sample. So I can take 2 times my standard deviation. But I'm basing that on this particular sample. This is going to be the uncertainty with this sample that I took. So I divide by square root of n. So these are 2 different days maybe, or 2 different sets of data that I've collected. One that gives me more control over the randomness by taking mini samples, and then I take another sample on the following day, but I use this standard deviation from a previous day or a previous set of experiments. Square root of n would be this n right here, and this uncertainty will be for just this sample, not this sample. All right, so this number comes out to be 2 times 566.3 divided by square root of 10, 358, plus or minus 358.16, and those are kilojoules per kilogram. And so what you see is these numbers gradually get smaller and smaller. Here, this is the uncertainty with the random uncertainty with one measurement. Random uncertainty, I've taken 10 measurements. Random uncertainty, that in the past I've taken a whole bunch of measurements, and now I've taken a new set and it's got a smaller uncertainty because I'm using the standard deviation from the larger set. So I'm more sure that this is the correct standard deviation, and I'm getting less and less certain when I take fewer and fewer samples. All right, let's see, what else did it want us to know? Estimate the total uncertainty of the mean value of the measurement, and then a single measurement. All right, so the mean value, the total uncertainty, we wrote that down. That's these guys. So the total uncertainty for the mean is we take B and we take the uncertainty for the mean. Now this one doesn't specifically say which of these, is it based on this sample after I've done a large sample, or is it just on this one? Let's just use this one. And let's assume that we haven't done the large sample. So total uncertainty for the mean. Let's write that. So this is our n equals 10 samples, assuming we never did the large sample. All right. U, or x bar, square root. Now we got to get that b, get on the page there, that b value. Remember how we were doing that for this one is it's this bias or systematic error, and right in here we had this information that the calorimeter has an accuracy of 1.5% of the full range. So we went and calculated that there's 1,500 kilojoules per kilogram that could just come from the tool itself not giving us the right measurement. And then this is for the mean, so we're going to take the 405 number that we had here, and calculate this guy. So let's see, we have basically just 1,500 squared plus 405.1 squared, and we're going to take the square root of that, 1553. So basically our we took 10 samples, we calculated a mean value for those 10 samples, and we would write that 49,180 plus or minus 1553 would be the total uncertainty, including the tools that we used to measure and the randomness just generated by taking the measurements, whether it's they change over time a little bit, or there's some human error, all this random stuff that might happen. That would be the uncertainty associated with the mean value of taking 10 samples. Now, if we only did one sample, so if we're talking about, one sample here, then the uncertainty with an individual sample is the same machine uncertainty. So this doesn't change. It's the same tool that we're using. Now, if we change tools or did something like that, then yeah, this number would change. Oh, there was a question, I don't know how long ago it was, but how do you get degrees of freedom? Degrees of freedom is just the number of samples minus 1. So right here, we'll come back to that in a second. Degrees of freedom is however many samples you take minus 1, and it's always that. There's no other way to calculate it. All right, so we were doing the total uncertainty for an individual measurement. The tool didn't change, so the bias or the offset error is the same. But when we calculated the uncertainty associated with a single measurement, we did have a different uncertainty. Here was for the group of measurements. Here is for a single measurement. And remember, it's the t value that, well, not just the t, it's the dividing by the number of samples, square root of number of samples. So plus 1280 point, well, 97, I guess we'll do that. And we square that. So 1500 squared plus 1280.97 squared. Square root of that is 1972. So it's plus or minus kilojoules per kilogram. And that is larger than the uncertainty associated with the group of measurements. So if I take and measure these 10 things, calculate their mean and standard deviation, and then pull out one of them, this 49,860, I'm not as certain of that individual measurement. But when I look at them as a group, you know, averaged together and their standard deviation, I'm a little bit more sure, this 1553, about this average. So, and it's, you know, it's common sense that if you do it more often, assuming you do the procedure correctly every time and you don't, you know, you don't have changes in your procedure or you change out your tools or some major thing that's going to affect the readings, then the more readings you take, the more certain you are you're getting the right, or you're honing in on this right answer. And it shows up in the way that the statistics work out. All right. I think that's the last that we're going to talk about uncertainty, I believe. We might do some next week, but for today, that's the last we're going to talk about it. We've got one other thing for today, and that's this idea of sampling rate. So it's not related to uncertainty at all, although it does introduce a different kind of uncertainty. Sampling rate. So sampling rate is not necessarily important for something like this, where these heating values probably aren't changing very quickly. They're probably pretty slow, and even our tool that measures them probably reads pretty slowly, and so I don't have to worry about this measurement not capturing this measurement because it changes so fast. Other signals do change quickly, like the sound stuff we were trying to do earlier. You know, the sound vibrates at anywhere from, well, I don't know, a human can hear somewhere around 50 hertz up to 15,000 or 20,000 hertz in hertz or cycles per second. So some of those are low enough, 50 cycles per second. I could probably get my Arduino without any real changes to it to measure that. 20,000 cycles per second, I couldn't measure that. I couldn't measure enough times with the Arduino. I'd have to have some other type of equipment. So we have to talk about this idea of sampling rate. I want to show a little video piece here. This is called the wagon wheel effect. So what he's got here is, and it'll make sense why we're doing this in a minute, but the wagon wheel effect is named after older movies that had wagons in them. So this would be like a wagon wheel. Now this is a particular pattern on one that's not a real wagon pattern. But what he's got here, this is just a disc of paper. He's got it hooked up to some little motor that he can control the speed. And there's some lines drawn here, kind of like spokes on a wagon, but they're not, you know, they're not patterned exactly right. And so he turns it on, and you can see now, I don't know how well it's going to show up being recompressed through YouTube and resampled again. So it may not look, you may have to go to Wikipedia and look at this yourself. But because it's going to get sampled again when YouTube compresses it. But what I can see, and what if you look at Wikipedia directly, what you can see is that eventually the outer wagon spokes are going counterclockwise, and the inner ones are, you might can resolve that those are going clockwise, or you're not even sure. Now it's more clear that they're going in now, the outer ones are going clockwise and the inner ones are kind of going counterclockwise, or you're not sure what the inner ones are doing. And he hasn't changed the direction here. He's only changed the speed that it's rotating. And they certainly shouldn't be rotating in opposite directions because they're printed on the same disk. Well, what this is, it's called the wagon wheel effect, but what it is called aliasing. And it's when, all right, and they're done with that. All right, we can close that. Oh, there's a game. All right, so the idea here is that we are experiencing aliasing. And what aliasing is you're looking, in this case we were sampling both through some video camera that captured this image initially, and then it's been translated to digital video, and now we're playing it back, we're streaming it, so it's been sampled a lot of times. It doesn't have to be sampled a lot of times for aliasing to occur. It could just be one time, but we've sampled it. We've taken individual snapshots of this video and we have played it back at some speed. And if we did not take enough pictures of the wagon wheel as it turns around, then we get these effects where it might look like it's going backwards or standing still. Like in an airplane hangar, they can't use fluorescent lights because it's possible that a fluorescent light, it actually flickers 60 hertz, 60 times a second, and the propellers on a plane could be rotating at exactly the right frequency to where it looks like the propellers aren't moving, but it's only to your eyes because it's kind of a strobe type effect. And you can walk into a running propeller because it's looks like it's standing still, but it's actually, or going really, really slowly, but it's actually spinning at a frequency that's getting sampled because the light's hitting at a certain 60 times a second, and you're looking at it and it's spinning 60 times a second, and it doesn't look like it's moving. That's the idea here, is that you misinterpret a signal based on how often you sample it. And there's a theorem, Nyquist theorem, that says your sampling rate, let me get the right letters for what we're going to call sampling rate. Well, I think we're going to use just Fs for sampling frequency. Yeah, we're going to use that. So Fs, that should be an F. Sampling, the S is sampling. Frequency. So how often are you taking measurements, basically, whether they're actual digit measurements or they're pictures or whatever they are. Sampling frequency has to be greater than 2 times Fm. So Fm is going to be the maximum frequency that you're trying to capture. Whoops, R. All right, so for instance, let's say this is your signal you're trying to capture. It's a sine wave like signal. It should be neater, but this is what we got. And we'll say that this is 1 second, half second, 1.5, 2, 2.5, 3, 3.5, 4 seconds. If you are sampling this signal every 1 second, so and that's really slow. So these can be 1 millisecond or 1 microsecond or whatever. Then you would capture one at 0, and then you'd capture 1 point here, and then 1 point here, and then 1 point here, and 1 point here. And it would look like, if you connected all the dots of what you sampled, it would look like it's 0. You know, if this is 0 volts, and maybe this is 1 volt, and this is -1 volt, it would look like 0 volts because you only ever captured it when it crossed 0. Now, if you captured it every half unit, half second. Then you add in this guy, and this guy, this guy, this one, and well, you get one over there. And so now it at least sort of looks like a sine wave, like if you connect the dots, right? Very jaggy, but it at least kind of captures the shape of the sine wave. But it's not, you know, it's not smooth like one. So this is maybe you've paid attention downloading a MP3 file or something. There's sometimes sampled at different frequencies. This is kind of what's going on. If you don't sample fast enough, then yeah, you can kind of reproduce the peaks and everything, but you're not getting everything in there. So it's kind of, it doesn't sound as clean, or it's kind of scratchy sounding. Well, it's because you sampled it kind of slowly and you only got the highlights. You didn't get all the smooth transitions. It's also the difference between listening to a kind of low sampled digital music and a record, an actual analog record where everything is captured. So the analog record reproduces everything in the sound, where the digital has to only get certain points. You can have a whole bunch of them in there, but it still doesn't get everything. Another problem, let's look at MathCAD. I have a MathCAD sheet here that's got, so we don't have to draw it every time. Let me see if I can find it. Here it is. All right. So let's start with this. Let me get my numbers set up right, and then I'll switch it over. All right. Here's MathCAD. What I've got is, I've got a 10 hertz signal right here. And then this is all basically how I'm going to plot the signal and sample it. I'm sampling at 1 hertz. So remember, this is hertz is cycles per second. So this would be a 10 cycle per second sine wave. Made it into a sine wave. And I'm going to sample it at 1 hertz. So first of all, that doesn't follow our rule here. Our sampling is supposed to be greater than 2 times our frequency. So I should sample at greater than 20 hertz if I have a 10 hertz signal I'm trying to capture. So one thing here is that you kind of have to have an idea ahead of time what is the maximum frequency you're interested in to know what to sample at. But here's the red line is the 10 hertz. So if it goes out to 1, you could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 peaks here. So it's 10 cycles in 1 second. And the blue line is if you sample it at the 1 second. So that's the thing that we drew the first time. So it's just the 1 second. So let's increase our sampling rate. Let's go to 3 hertz. So now I'm still not obeying the Nyquist theorem, but I am sampling faster than I was. So now what I get is I get something that kind of looks like a sine wave, but it's totally the wrong frequency, right? You know, if I kind of interpolated between these with a smooth line, then I would have a sine wave like shape, but it would be 1 hertz. It would not be, or maybe it wouldn't even be 1 hertz. I think it'd be about 1 hertz. It wouldn't be 10 hertz. So I would have aliased the 10 hertz signal down to a 1 hertz signal by sampling at the wrong rate. And I wouldn't know the difference unless I was ahead of time sure that I was looking for a 10 hertz signal. I would think, oh yeah, I found the signal right there. It is right there. And I would think it's a 1 hertz signal because it has 1 cycle in this second. If I did, let's do 6. Now I get something that might interpret that as 2 hertz, right? So there's 1 sine and then or another one. So I would get a 2 hertz sample, a alias. And the word alias, remember, it kind of means like an alternate identity. You know, you might hear it in like spies and espionage and stuff like that. But that's what it's talking about here. Is it's also known as, but in this case it's fake. You know, I think I see a 2 hertz, this blue line signal, but I'm really trying to measure a 10 hertz signal. I'm just measuring it too slowly. Let's go to actually 20 hertz. So this would be almost the Nyquist theorem, except Nyquist says it needs to be greater than 2 times the maximum frequency. And I end up with another one of these where I measure 0. So let's go to a little bit, let's go to 22. All right. Now I at least have all of the information there about the frequency, but I don't have the amplitudes right. So this is where there's another part to the Nyquist theorem. The first part is the one we wrote down, that the sampling frequency has to be greater than 2 times the maximum frequency. So we have that here. But the part that I didn't write down is that and you have infinite, let's just do infinite sampling time. So if you have both of these, then you can reconstruct the original signal. So if I took this and I sampled it over and over and over and over for a long period of time, maybe not actually for infinite time, but for a long period of time, I could eventually mathematically reconstruct the 10 hertz signal and its amplitude. But generally what you want to do is, well, you can't sample for infinite amounts of time. You have to sample really quickly and then analyze the results. So, because it might be part of a control system or something that has to do this on the fly. So in that case, I need to make my sampling way more than 2 times the maximum frequency. I might have to go up to, I was at 10, so I might have to go up to 80 hertz. And now I don't have a perfect representation, but I have the amplitude is captured. You know, I've got the peaks at where the red peaks are, the blue peaks and the red peaks match up, and the frequency matches up. So if you don't have infinite time to sample, then you have to sample at a much, much faster rate than what Nyquist says. So I'm at 80 hertz now. If I do 100, then it gets better. Oh no, actually 100 actually got worse a little bit. I lost the amplitude a little. You know, it doesn't quite have the right peak there. So it is possible. There's all sorts of issues with sampling and sampling fast enough. And at some point you get to where your tool, in this case we're using Arduino, which is actually really slow, but your tool cannot sample any faster. So there are some signals you just can't measure. So there are some things you can do to help though. So you do have to have an idea of what frequency you're trying to capture. So you want to capture 10 hertz. So if you know that you want to capture a 10 hertz signal and you're not really interested in anything above that. So the higher order stuff, if there's a 20 hertz signal, or there's always a 60 hertz signal, because that's what, in the United States, that's what our electricity operates at. So there's always 60 hertz noise around you from lights, from electrical outlets, from all sorts of things. If you live near a radio tower, you're going to get interference from that. So there's always higher order frequencies out there just in the air that you're going to capture, unless your device is very well shielded. So what you can do is remove the higher order frequencies, so filter them. We're not going to talk a whole lot about filtering, but there are digital and analog filters out there. So you can build filters with op amps, you can build them with resistors and capacitors, you can build them into software to filter them out, because what will happen is that 60 hertz signal that is unwanted, if I only want 10 hertz, then the 60 hertz will actually alias down, you know, to a potentially, it could alias to a 10 hertz signal, or it could alias to something that interferes with what you're doing. So even though you can't capture the 60 hertz because your machine is too slow or whatever, then those higher frequency signals might alias down just the way this one did when it went from 10 to 1 or 2 or whatever, or 0 even. and show up in your signal. So you build a filter to get rid of anything higher than what you're looking for. So there are high pass and low pass, band pass, and notch filters, all these types of filters that we have to deal with. I don't know that we'll actually get to build many filters in here. That they're kind of a point for another class. I don't know if we'll be able to do that or not. Maybe we can at least look at what they'd look like. Not today. Anyway, these filters can knock off those higher order things. And then you are left with just, can you sample fast enough? Now the Arduino in its base form, without doing any special tweaks to it, is only going to sample maybe, I think you can relatively easily get it to sample at 100 hertz, maybe, which would mean you really can't sample anything much faster than 10 hertz or something like that. If we did, well, 110 is what we have right here. If we change our frequency to 20, what does it look like? Technically, this would still work, right? You just lose a little bit of your amplitude, which a lot of times the amplitude is not as important as the frequency. We can get the frequency of a 50 hertz signal, right? Well, no, a 49 hertz signal if we're sampling at there. So there's our frequency we captured, but our amplitude is not there at all without being reconstructed, which means we would have to sample for a long period of time. There is the idea of what's called a folding diagram. What this will do, let me see if I can find one. Don't change. Here's one right here. So this is a folding diagram. It looks like it's really complicated, but it's not. In fact, we'll use it here in a second. Oh, I'm zooming the wrong way. Wow, I'm zooming all over the place. So it has 4 different numbers on it. FM, we already talked about that. That's our maximum signal, the 10 hertz that we were trying to capture before. FA, that's the alias. So what could the 10 hertz show up as if I don't sample fast enough? FN, here and here, that's the folding frequency, which is just your sampling frequency divided by 2. So that's coming from the Nyquist theorem. So for instance, let's see, I don't know if I can get all of this on the same page at one time. Maybe I can, we'll see. So I'll come back to our page once we get all this stuff written down. So our alias frequency is what we're trying to solve for. Our maximum frequency, let's say, is 10 hertz because that's what we were trying to solve, trying to capture. Our folding frequency is our sampling frequency divided by 2. Let's say we sample at 2 hertz. So our folding frequency is 1. I don't know. I don't want to use 1. Let's make it. Well, no, we can use 1. It'll be fine. So we sample at 1 hertz. Well, no, we sample at 2 hertz. Folding frequency is 1 hertz. 2 divided by 1. And then, like I said, our sampling frequency is 2 hertz. All right. So this is all I wrote down. We don't know our alias. This is what the signal that we're looking for might show up as. We want to find a 10 hertz signal. Our folding frequency is 2 hertz, our sampling rate divided by 2, so it's 1. All right. So on the chart, you have this little ratio here, maximum over folding frequency. For us, that's 10. Oh, wait, 10 is not going to show up on here because it goes off the chart. It ends at 5.8. We'd have to have a larger chart. Let's change our sampling rate to something so it'll show up on our chart. Let's sample at 6 hertz. So I changed my sampling rate to 6 hertz, which changed my folding frequency to 3. And then M over N, so the maximum 10, divided by my folding frequency of 3 now, because I changed my sampling rate to 6 hertz, is 3.3. So I go up here looking for 3.3. There's 3.2, there's 3.4, so 3.3 is this line in the middle. And then I drop down to this number, 0.7. So that is, if you notice the x-axis down here, FA over FN equals 0.7. If I had a FM maximum 10 hertz divided by folding frequency of 3.3. So I went up to 3.3 and came down to 0.7. And 0.7 equals the alias divided by folding frequency. So my folding frequency was 3. So 7, or 0.7 rather, 0.7 times the folding frequency of 3 is an alias of 2.1 hertz. So what this says is that if I sample a 10 hertz at 6 hertz, so I didn't follow Nyquist, I couldn't for whatever reason sample fast enough, my folding frequency becomes 3, and I end up with a alias to folding frequency ratio of 0.7. So folding frequency is 3. 3 times 0.7 is my alias. That 10 hertz signal will show up as a 2.1 hertz signal. This doesn't really help you, but it does tell you what higher order or higher frequency signals will show up as, will alias as. So it gives you a bit of information. There's not a lot you can do with that information other than to know that, hey, that 10 hertz signal is probably being aliased as a 2 hertz signal if I don't sample fast enough and I sample at this rate. So these folding diagrams, they're more for what we're going to do. They're just kind of a academic thing, just so that you know that the 10 hertz signal showed up as something that it's not actually. This is its alias, basically. All right. I think that's what we need for now for sampling rate and that uncertainty stuff. We talked about the little speaker. We have next time on Tuesday, we're going to build the op amp to amplify our strain gauge. So hopefully you've got your strain gauge, Wheatstone bridge, and strain gauge working. If not, it's not super important unless that was the sensor you're going to use for your project, and then you got to figure it out. The op amps are the op amp circuit that we're going to build is just a useful circuit in general to be able to amplify smaller voltages. There are all sorts of arrangements of op amp circuits that you can create to do different things. We're going to use one that's just going to be a multiplier, but there are a lot of other things you can do. In fact, you can use that op amp to do some filtering work that we won't do right away. All right. I think we're pretty close to done with the content for the quarter. A lot of the rest of the quarter is going to be you collecting data. There are some homework assignments still, but collecting data on your project. You're trying to get 3 days worth of data, and then figure out what it actually shows you. I didn't see anybody who was trying to sample anything that they couldn't sample, where you'd run into these sampling rate problems. I'll look again and see if there were any, but I don't remember any that would have sampling rate problems. You really have to sample a very quickly changing signal, which would be tough to do over 3 days, right? Because you'd have just huge amounts of data that you just couldn't even store, possibly. So we'll be back on Tuesday, and we're getting close to the end of the quarter. A lot of it left is project work. There's one more exam, and maybe one quiz or 2 quizzes left on the little podcast thing. The podcasts are there to just give you a case study of how some of this stuff plays out in the real world. So they're all real world examples. They're not just academic, things that we make and force to happen. They're actual things that did happen. All right. I'll see you on Tuesday. And if you have questions, let me know.